In this video, we continue the lecture to part 3. A coloring for a graph is an assignment of a color to each vertex in such a way that if you have vertices that are joined by an edge, they will have to have different colors. Let's consider this graph, and this might be a different way that you see graphs represented. Instead of having it look like this with the closed vertices, just to see the coloring better, A, B, C, D, these are exactly the same, except sometimes we might have a bigger open circle with the label inside as opposed to the dot representing the vertex C with the label outside. Now, if we were going to give this graph a coloring, the idea is not that we just color it however we want, but we fit the criteria that if two vertices share an edge, then they can't be the same color. So what I think is nice to begin with is to find one of the vertices with the largest degree. And as we look at this graph, vertice A, B, and C all are degree 2, whereas, A and B are degree 2, C is degree 3, D is degree 1. So C has the largest degree, so let's color it first. And if I color it yellow, then to make it a true coloring, any other vertice that shares an edge with C can no longer be yellow. So for instance, B could not be yellow because it shares this edge. A could not be yellow because it shares this edge. D could not be yellow because it shares this edge. Next, we continue to find the next vertice of highest degree that's remaining. Now the two remaining vertices of highest degree are A and B because they're both degree 2. Let's color A first. So let's say I color A green. So I'm choosing a different color because no other vertices can have the color yellow because they all share edges with C. Now if I color A green, notice B cannot also be green because they share this edge. However, D is not connected by a single edge to A. Now you could go from A to C and then C to D, but you couldn't go from A to D in a single edge. So since these are not connected by a vertex, they can be the same color. So we could color D also green. That fits the criteria. Now what remains is, again, B can't share a color with A nor C, so we can give it a different color, pink. And this is a valid coloring. Next, let's look at something that would be considered an invalid coloring. So I'm going to draw in this graph to apply colors, and it's not going to be a proper coloring. Consider to yourself why this is an invalid coloring. What is the problem here? I recommend you pause the video so that you can take time to identify the issue. The issue is here. Notice that we've got a single edge, and on either side of the edge you've got the same color. But to truly be a coloring, sorry, that edge needs to be there. To truly be a coloring, if you share an edge, you can't be the same color. So we would have to change the coloring of B to make it a different color in order to make it valid. So to make it a valid coloring, we could maybe consider B to be orange, something like that. Now that we've talked about the basics of what would make something a valid coloring, let's look and turn to the idea of a chromatic number. Okay. Now, there are many ways to give a coloring for a graph. And because there's many ways to have a coloring for a certain graph, we might want to consider what is the most efficient way to color a graph, and what way could we color the graph and use the least amount of colors, and that's represented by the chromatic number. So the chromatic number of a graph is the least number of colors needed to achieve a proper coloring. So if you use any less than the chromatic number, it's no longer a valid coloring. So that'd be the idea. keyword here is least. Now the steps for coloring a graph recommend that you first choose the vertex of greatest degree and give it a color. Then use that same color to color as many of the remaining vertices as long as you can do so without coloring two vertices the same color if they're joined by an edge. Then, since you've done all that you can with that color, you would choose a new color and repeat step 1 for all the vertices not already colored. Keep doing this until all the vertices are colored, and that should give you least coloring, so long as you're making sure that at each step you are applying the color as many times as you can, so long as they're not the same color if they're joined by an edge. Now we have two examples here where we have different graphs drawn and we're asked to give a coloring. Now here you're definitely going to want to have a variety of colors of highlighters or pens, pencils, crayons. And one thing that you could do if you don't have a highlighter handy, although I definitely do recommend finding it, is first you should copy this down on your paper just to make it clear. These are the vertices. So it has 7 vertices in all, and for this graph these are the vertices. Okay. So I'd write these down, and if you don't have multiple colors, you might try to just label it like color 1, so on and so forth, but if you do have it, it will help the visual here. So to begin with this example, we want to identify which of these 7 vertices has highest degree. So find the vertice of highest degree. Pause the video until you find it. So the vertex of highest degree is this middle vertex. It has degree 6 since there are 6 edges coming from it. So I'm going to apply this has the coloring yellow, and then I'm going to look at the remaining 6 vertices and ask myself, can any of them also have the color yellow? This one can't be colored yellow because it shares an edge. This one can't be colored yellow because it shares an edge. So none of the other vertices can be colored yellow because they all share one edge with the yellow vertice. So now we need to pick a new color, let's say green, and find the next highest vertice of highest degree. This is degree 3, 1, 2, 3, 4, degree 4, 1, 2, 3, 4, degree 4, degree 4, degree 3, degree 4. So whenever they're tied, just pick one of the ones that's tied for highest. Let's say this one, and that should be green. And we ask ourselves, of the remaining 1, 2, 3, 4, 5 uncolored vertices, who can share this green? This one can't because they're connected by an edge. This one can't. Okay. This one can because notice it's not connected by a single edge. It's connected by one to here and then one to here, but there's no direct connection from here all the way to here so they can be the same color. Okay. While this and this vertice are not directly connected, it now shares an edge with this green one, so it can no longer be green. So you have to consider, if now that we have these both shaded green, this couldn't also be green. This can't be green because it's connected there. So then we still go to the next highest remaining uncolored vertice, choose a new color because we've exhausted the use of green. Maybe we'll next color this one. Okay. Now we've got 1, 2, 3 remaining uncolored vertices. This one can't be pink because it's connected by a single edge, but this one could be. The remaining one, though it's not connected to this one by a single edge, it is connected to the other pink. So now we pick the next highest remaining vertice. These are both tied for degree 3. So let's just pick one and color it orange. Okay. These two vertices, there's only one more uncolored. It's not directly connected to this by a single edge, so it could also be orange. So we gave this a coloring with as few colors possible, and then remember the chromatic number is just the least number of colors that needed to be used, and here we've got 1, 2, 3, 4 different colors used. So 4 is the chromatic number for this graph. Now for the next example, you're asked for this graph to color using as few colors as possible, then find the chromatic number based on what you colored. I recommend you take a time to attempt this on your own, draw the graph correctly on your paper, apply a least coloring, and then unpause to check your work. To begin, you always try to identify which vertex has highest degree. Now this graph has 6 vertices in all, and this vertex are both degree 5. They both tie for it. Let's just first work on this vertex. Now we pick yellow here to the highest degree vertex, and of the 5 remaining vertices, we want to see if anybody else can directly share yellow. This is connected by an edge, so it can't. Connected by an edge, 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 and then an edge around here, so nobody else can share yellow. This is the next highest remaining color vertex. We'll give it a different color of green. Can't here. Okay, so this vertex is connected to all the other vertices, so no one else can share green. Pick a new color and find the next highest degree, degree 3, degree 1, 2, 3, 4. 1, 2, 3, 1, 2, 3. So this is the next highest remaining. Give it a coloring. Share so it can't be pink. Share so it can't be pink. But if we look carefully, we see that this vertex is not connected by an edge to this vertex. So these could be the same color because they're not connected by an edge. Now the remaining vertices, this one also has 4, so we'll color it next. Let's color it orange. Connected here, 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 here. Notice it's not directly connected to this vertex through any of the edges, so it can share the same color. So we've given a coloring with as few colors possible. Now there are many correct colorings. So if you did this problem while it was paused, yours might not look exactly like mine, but there should be 4 colors, and you should verify that on your graph, if vertices are connected by an edge, they can't be the same color. And if you have questions about that, feel free to send me a picture of your work through Canvas inbox, and I'd be happy to check it for you. Now from this, we've used 1, 2, 3, 4 different colors. So the chromatic number for this example is 4. Now, whenever you're coloring your graph, there's a very interesting result if you consider maps like we might see in a geography class. And what we're going to do is we're going to consider that if 2 countries share a border, that's the same idea as having those 2 countries as vertexes and sharing an edge. And thinking that way, it was proven in the 1970s that for any map you could draw, you would need at most 4 colors to give it a correct coloring, where if 2 countries share a border, they can't be the same color. And that's what's known as the 4-color theorem. So for our example here, we are going to show that we would need 4 or less colors to give this map a proper coloring. So it will be a correct coloring if anything shares a border, they can't be the same color. So for instance, A and B can't both be yellow because they share a border. But for instance, A and F could both be yellow because they don't share a border. Now we could turn this map into a graph where the relationship is for each country, we gave it a labeled vertex, and countries are connected by an edge if they share a border. So for instance, A shares a border with C. We show that by making an edge between A and C. A shares a border with D and with B. And take a moment to pause and just verify for yourself that this map is equivalent to this graph if we let every country be represented by a vertex and shared borders represent an edge between the 2 countries. Now, one of the reasons that we might want to represent this map as a graph here is I think it's going to be a bit easier to give everything a proper coloring, because now we can quickly, based on reading how many edges come out of each vertex, find the vertex of highest degree and give it a minimal coloring as we did in our previous example. So take a moment and pause the video and identify which of the countries, which vertex has highest degree of this graph. So D has degree 5, B has also degree 5, as does F. Let's just pick one of these to color. Maybe we would first give F the color yellow. And remember now, once you've given one of the vertices a color, you say, do any of the uncolored vertices, can they share that color? i.e., are there any other vertices that are not directly connected to F? G is connected, H is connected, C is connected, D is connected, B is connected, but for instance, E is not directly connected to F. Also, A is not directly connected to F, nor is it directly connected to E. Now we might look at our remaining vertices, B, D, C, G, H. D and B are still the highest remaining vertices, so let's give D a color, green. C can't share that color because it's connected, nor can B. Okay. But D is not directly connected to G, so it could share that color. Now, while D is not directly connected to H, H is connected to G, so it can no longer share the color green. Of the remaining uncolored vertices, we've got B here. Okay. C is not directly connected to B, so C can share the color. Now, H is directly connected to B and C, so it can't share the same color. So then our last vertice, H, can't share any of the earlier colors because it's directly connected to a vertice that shares that, but we could give it a new color, orange. Okay. And with this, we have colored this map like so.